Good afternoon, ladies and gentlemen. I'm Aldo Febriansyah Putra. First of all, I would like to say thank you to the TPC of IAGI for giving us an opportunity this year to share our study on the subsidence mechanisms and fault development in the Ombilin Basin. And we also would like to thank to all of the audiences who make your time to join the session. Let us begin first with the school of thoughts regarding the origin of Ombilin Basin. The previous study in this area suggested that the Ombilin may originate as a pull-apart basin or as a reef basin models. And the third model created by Hussein et al. Uh, suggested another view of interconnected graben between the Payakumbuh and the Ombilin Basin. And in this study was aimed to give an alternative to the school of thoughts regarding the origin of Ombilin Basin. So we will see an alternative idea of how this basin forms and how this basin deform. Ombilin Basin is principally located in the western part of central Sumatra. It is located in the high Barisan Mountains, located side by side with the Lake Singkarak Sumatran Fault. We use two groups of data. The first is the remote sensing data. We use Aster Global Dam to help us regarding the surface interpretation. And the second, we have subsurface data. We have 2D reflection seismic sections worth about 456 kilometers. When we also have well data, it included the wireline logs, VSP, biostratigraphy, and geochemical reports. We use this data to build our interpretation. The method we used was first the remote sensing interpretation. We identified surface fault lineaments using the DEM data. And then we did subsurface interpretation. In this context, we used well log and seismic interpretations. And then we also performed the subsidence analysis to construct the subsidence mechanisms. And then the last, we performed parasympathetic reconstructions to reconstruct the fault development in the study area. Let us first begin with the big picture of Sumatra. This region was constructed by at least three terrains. As we know, the Sibumasu terrain in the east, and then West Sumatra block, and we have the Woyla Arc in the westernmost part of the island. The accretion of Sumatra ended in the Mesozoic, precisely in the late Cretaceous, and it gave Sumatra the pre-existing structures, the northwest-southeast trend that we commonly have in the Barisan Mountains. Ombilin Basin is located in the Barisan Mountains, so we have a tertiary basin in the mountainous region. In this case, we can see that the Ombilin Basin may be the western continuation of the Central Sumatra Basin. And in this case, we see that the major fault controlling Ombilin Basin in this case is the Takung Fault in the northeast part of the basin. We will see more precisely later in this session about the evolution of the Takung Fault. This is the geologic map and also the schematic model of Ombilin Basin regarding its sedimentation. Ombilin Basin started in middle Eocene. It was characterized by the lacustrine sedimentation of Sangkarewang Formation, and also we have alluvial fan deposition of Brani Formation. And then subsidence continued, and we have sedimentation of the Sawah Lunto and Sawah Tambang fluvial deposits. And then as we enter the Neogene, as we enter the Miocene, we have marine deposition of the Ombilin Formation. So there is the short summary on the stratigraphy and sedimentation of the Ombilin Basin. This is the result of our study. This is the fault lineaments of both the surface and the subsurface. As we see in this map, we have three major trends in this basin. The first one is the northwest-southeast trend, as we see on the map. This is the prominent trend in the study area. We have Takung Fault as the major fault in the basin trending in the northwest-southeast, and we also have north-south and the northeast southwest trends in this basin. So as we see on the DEM data, the Takung Fault made a distinctive morphology, just as the north-south Tanjung Ampalo Fault. We have a steep fault scarp because of that structure. This is a seismic section trending southwest to northeast. So we see the section is crossing the major structures in the area. In the seismic section, we can see that we have an inverted half graben structure. In this case, Takung Fault was represented by Sinamar Fault. This is the subsidiary of Takung Fault, and it faced towards the southwest. And we also can see that the Eocene and Oligocene units thicken towards the Sinamar Fault, which means that the two units deposition was contemporaneous with the fault development. And we have the intra-early Miocene unit, which appears to have a parallel refractor. And then we move a little bit to the southeast. We have a similar inverted half graben structure, but in this section we can clearly see the positive flower structure as the continuation of the Palanki anticline. And in this case, Takung Fault was represented as Sijunjung Fault in this section. As we compare with the previous section, the Sijunjung Fault is facing in the opposite directions compared to the Sinamar Fault. So we can regard that the two Sinamar and the Sijunjung faults are as the subsidiary of the major Takung structures. And we can also see that the Eocene and Oligocene units, both of them thicken towards the Sijunjung Fault, a similar phenomenon that we used in the previous section. And the intra-early Miocene unit is thicker between the Palanki and the Sijunjung faults. We will address this evidence later in the geohistory part. And this is the section that runs parallel with the major structure. In this section, we can see that the northeast-southwest structures was reactivated, and we have positive flower structures in this section. So on the other hand, we can also see that the Eocene and Oligocene units was controlled by the fault Fy1 and the fault Y2. So both the Eocene and Oligocene units were fault controlled. And then we have a widespread intra-early Miocene sedimentation. As we get back to the fault maps, we can regard the northwest-southeast Takung Fault as the major structure of the basin. And in here, Sinamar and Sijunjung faults were the subsidiary structures of the Takung Fault, and we can regard them as the synthetic and antithetic branch of Takung Fault. The other northwest-southeast structures, we can regard them as the secondary structures of the Ombilin Basin. And then the north-south and the northeast-southwest faults, we can recognize them as the transverse faults of the basin. These are the faults that crossing the basin. And then we move to the geohistory chart. This geohistory chart, we aim to show you the evolution of the basin since its beginning in the Middle Eocene. As we see, the basin started in Middle Eocene, and then we have rifting until the late Oligocene. And then we have a transient uplift in late Oligocene, which removed about almost 600 meters of sediment thickness. And then subsidence continued, and we have marine environment developed in the early Miocene to late Pliocene. Actually, the succession that was recorded in the Ombilin Basin was only until early Miocene. We interpreted the marine sedimentation to continue until late Pliocene based on the regional uh, based on the other regional study that the contribution of Barisan Mountain sediments towards the Bekak Basin was uh, starting in Pliocene. So we decided that the late Pliocene could be the end of Ombilin Basin sedimentation. And then the latest uplift in the study area removed sediment thickness of about 1,100 meters. And in the determination of in the estimation of the eroded thickness, we use filternate reflectance. Uh, in here, we perform backstripping analysis. Backstripping analysis was attempted to remove the seawater and sediment thickness effect on the total subsidence. So we could derive the tectonic subsidence of the study area. As we can see in the chart, the period between the middle Eocene to late Oligocene, in that period of time, we have fault controlled subsidence with the maximum depth to reach 1,700 meters. And then it was interrupted by an uplift, and then we have the thermal subsidence. This subsidence occurred in a longer period of time than the previous one, and it reached about 2,300 meters depth. We converted the tectonic subsidence chart into rate, and as we see in this chart, the fault control subsidence actually was increasing from the middle Eocene to late Oligocene. So we have uh, accelerating basin subsidence because of fault in that period of time. And then it was interrupted by uplift, and then we have thermal subsidence. As we see in this chart, the rate of thermal subsidence was gradually declining. So probably this is the effect of the thermal decay during the subsidence. And then also we have uplift in the late Pliocene. This is the chart provided by Allen and Allen. It considered the backstrip tectonic subsidence rate and duration of subsidence to give regard on the basin types. As we see in this chart, Ombilin Basin can be regarded as a reef basin based on the tectonic subsidence. However, as we consider other classification, in this case we use C and Heller, Ombilin Basin does not show slow long-lived subsidence of a reef basin that is stated by C and Heller, but its duration of subsidence is far longer than the common Straxley Basin. So Ombilin Basin is actually lying between the Rift Basin type and the Straxley Basin type. And we will use paleosphatic reconstruction to address this issue. And here, this is the structural configuration of Ombilin Basin in the Eocene and Oligocene. In Eocene, we see that the basin rifting occurred in the Eocene, and then in the Oligocene, the rifting continued. But the interesting part of this reconstruction is that we have that the Eocene unit was folded because of during the Oligocene sedimentation. And this folding provided us that the evidence of strike slip component during the rifting of Ombilin Basin. So this is the evidence that we have to regard that Ombilin Basin as an oblique reef phenomenon. And then we have uplift in the late Oligocene and also widespread sedimentation during the Neogen. And then we have the uplift in the late Pliocene, and this is the recent configuration of the Ombilin Basin. So we can compare that previously we have an oblique reef, and then at the present time we have the inverted structure. We have positive flower structure over here, and then based on this evidence, we consider Ombilin Basin as an inverted oblique reef. As a conclusion, Based on our consideration on the subsidence mechanisms and fault development, we would like to regard Ombilin Basin as an inverted oblique reef. And this is Ombilin Basin actually a nice example of studying a basin evolution, because we can see the fault evidence both in the surface on the geomorphology, and also we can see them in the subsurface. We would like to say thank you to geoscientists and management of PT Rizky Bukit Barisan Energi for the subsurface data access and discussions. And also we would like to thank several people, Pak Tio, Bu Yara, dan Pak Salahuddin Hussein for the discussions. That's all my presentation. Thank you and have a good day.